So I told you that the cones in the center of your vision allow you to see fine details. But in the periphery of your eyeballs, you only have rods, and rods cannot see fine details. And I'm going to prove that to you right now. So there's nothing unusual, just flashed pictures, right? Different faces, they're all well-known people. Nothing's going on here. Now, you see the white cross in the middle? Now I want you to look at that white cross, fixate it, look directly at the white cross, and notice out of the corner of your eyes, out of the sides, out of your peripheral vision, out of your rod vision, what the faces look like. So put your fovea right on the X and let your rods, the side vision, see the faces. Don't the faces look weird? Don't they look like cartoons? You can look directly at the faces, they're normal. But when you look at them out of the sides of your eyes, in your periphery, they're distorted. That's because your eyes cannot see clearly in your peripheral vision. So isn't that amazing? You can see clearly where you're looking, but on the sides of where you're looking, you cannot see clearly. Normally, your brain is able to make a guess as to what's on the sides. But if you haven't had a lot of experience with it, if you haven't fixated it repeatedly with your eyeballs, then the information that your rods take in is not as detailed. And so that leads your brain to come up with some strange distortion. Hopefully you've understood now that your vision is dependent on two kinds of photoreceptors. One that's nighttime vision, rods, works in shades of gray and does not have high details. And the other is our daytime vision, relies on cones and has color and high detail. Normally, during daylight hours, we rely on cones. It takes us about, honestly, 20 to 30 minutes to be able to shift from our daytime cone vision to our nighttime rod vision. And that's indicated in the graph here. The first 10 minutes that you're in the dark, you're still relying on your cones, so you can't see well. After a few minutes, you can see more clearly. And you may have had that experience at a movie theater or driving through a tunnel. It's called dark adaptation. You're in a bright, sunshiny place, and then you walk into a dark room, like a movie theater or a long tunnel. Now, when you first get in, you can't see anything. Why? Because you're still relying on your cones, and your cones don't work well in low light settings. So for example, when I go to the movie theater and I first walk into a dark room, I have to fumble around a bit because I can't see the other people in the room. I can't see the chairs. I don't really know where I am. But then after I sit down, after about 15-20 minutes, I notice, now I can see where all the people are in the room. Why? Because my cone vision has quieted down and I'm relying now on my rod vision. So now I can see in the dark with my rods, whereas when I first walked into the dark room, I couldn't see with my cones. Pilots have to be really careful of this, and flight school always covers this topic. During the daylight hours, pilots rely on their cone vision. They look at whatever they need to see with fine detail. But in nighttime, their cones don't work. They have to rely on rod vision. So you have to look about 5 to 10 degrees away from whatever it is you want to get information about so that your rods can pick it up, because your cones can't work when it's too dark. Okay, you know now, cones are in the middle of your retina, rods are in the periphery. Cones are sensitive to color. That means when you look straight ahead, say looking at my face, your cones are processing this, and the sensation is colorful. What's around, if you imagine what was around my face is a giant donut, that is actually vision that is not colorful. It's actually grayscale, white and black and everything in between, because it relies on your rods. The way we don't experience the world this way, and that's because our brain is constantly filling in information. It's constantly predicting what would be there. So you are actually colorblind in your peripheral daytime vision and in your night vision. You're just not aware of it. So when you ask somebody else, what's it like to be colorblind? That person could ask you back. It's no big deal. Okay. Your photoreceptors have axons that connect to the brain. So the retina is not a Wi-Fi system. It needs a cable that connects the information extracted from the photoreceptors and sends it back to the occipital lobe for processing. That cable has to exit your eyeball, so it needs a hole to do that. And we call that hole the blind spot because there's no photoreceptors in that cell. All there is a nerve, the optic nerve, and also blood vessels, because the cells in your retina need blood just like the cells in your brain. So there's a spot in each of your eyes where you are blind because there's no photoreceptors in that spot. The only thing that's in there is your optic nerve and blood vessels. Here's a picture of a human eye where you can see the blind spot. It's that orange disc. And you can see the blood vessels going in and out of that hole in your eye. You can't see the optic nerve, but you can see the blood vessels. So what does that mean? It means that in each of your eyeballs, there's a place where you're blind. Why don't you see that blind spot? Well, in my class, we're going to do some demonstrations that allow you to see what happens to information that falls on your blind spot. But the answer of why we're not consciously aware of these big blind spots in our eyes is that our brain is using the information that's elsewhere in the retina to make its best guess as to what information is where the blind spot's not recording it. Okay, color perception. Have you ever heard the term colorblind, that someone is colorblind? What does that mean? That's what we're going to get to now. Most people, and by most people I mean 99.6% of women and 91% of men, have three kinds of cones. Cones that are sensitive to short, medium, and long wavelengths, or informally blue, green, and red. But not everybody has three cones. Those of us who have three cones, it's the relative activity of those three cones that tell us what color we're looking at. So if my blue cones are responding really strongly, but my green and red cones are not, then I know I'm looking at the color blue. People who we call colorblind, the vast majority of them see color. That's why the term colorblind is a terrible term, because it makes you think that some people who are colorblind cannot see color. The vast majority of them can, because two cones is enough to see color. Now, because there's three cones typically, it turns out there's three kinds of dichromats, or three different ways to be colorblind. Your short wavelength sensitive cones could be dysfunctional, or your medium wavelength cones could be dysfunctional, or your long wavelength cones could be dysfunctional. And on the graph here, what I'm showing you is what color looks like, a simulation of it, what color looks like for trichromats, that's on the far left, and on the right is what the three different types of colorblind, or dichromats, two cones, dichromats, how they see the world. And you can see by comparing them that, for example, people who are missing their red cones have trouble seeing red. People who are missing their green cones still see some green. It's more of a khaki, I think, but they also struggle with red. People who are missing the blue cones, interestingly enough, can see red just fine, but they really struggle with yellow and green. So there's three different kinds of ways to be colorblind, which means really not the absence of color, but the perception of a different kind of color. If you have a dog, you might be interested in knowing that dogs are dichromats, and they experience the colors of the world as you see here. Okay, that's it for vision. Students in my class, head back to Canvas and do the labs. Thanks, everybody.